Hi folks, this is the video tutorial for homework 3 of lab section 54. And two problems are given, but you're asked only to turn in homework number 2. So let's start with homework number 2, and it looks like this. So you have let me zoom out. So you have a Belleville Spring. This is called a Belleville Spring, and you put it on the ground or something, and then you push on it. You put something on it, and it compresses this top ring. Okay. So the dimensions of given made of steel, and let me see now. There is uh, this R1 and R2 are given here. This is 0.75. This is 2 inches, and the height is zero point 0.5. Okay. So what I'm going to do is I'm going to create that shape, but I'll take only 90-degree sector of it because it says you'll use only a 90-degree sector, because any sector that you take, 30, 45, 90, 60, etc., it behaves the same way. I've been in 90 here to make it easier for you so that you don't have to use the local coordinate system, okay, or axis system, okay? And then once you create those edges, free edges, then you restrain them for symmetry consideration. And we are assuming that the bottom is sitting against some flat surface, rigid surface, so it doesn't move up and down, but it can still bend, okay? It can still kind of rotate. So let's go ahead and do this. 0.75, 2, and zero point 0.5. Okay, so let's start with the CATIA file. uh, File new, part file, immediately save it. So file, save management, save as, desktop, new folder. This is homework 3, lab 54. Everything is going to go in here, both problems. And let's give it a meaningful name. So this is going to be your student ID number, 1, 2, 3, 4, 5, 6, 7, 8, 9. Your last name, Bernoulli. This is homework 3. Homework 3, problem 2. This is problem 2. And this is lab 54. Lab 54. Okay. Okay, so let's make the part. Here is how I'm going to do that. On a convenient plane, on that vertical plane, I will sketch. I'll draw a slanted line. That slanted line will be basically this line that you see here. This line, okay? So, change my units. Tools, options. That's because when I did a video for section 53, I changed some stuff to metric units. So inches, okay, pressure or force, pound force, and pressure, change it to psi. There. Okay. So let me draw the line. A line like this. Suppose that. Let's give it the dimensions that we want. So the distance from this point to that line is 0.75. Okay, the distance from here to that line is 2. And this height, the distance from here to here, vertical, right click, vertical height. Control Z, Control Z. Right click, uh, vertical. Okay, I think, what do I have there? 0.5? Is that right? So let's see now. This height is, H is 0.5. Very good. Very good. So we say, okay, now I'm going to take this thing and I'm going to exit. First of all, exit it. And then I'm going to shaft it. This is extrude. I don't want to extrude it. Look for shaft. You'll find it. I don't see it here. I don't see it here. Okay, so Katia calls this thing actually revolve. I think he's calling it revolve. Let's see if we can find it. If not, then I might have closed it because I didn't think I was going to use it, so I might have closed it. So let me remind you how to reset your toolbar. So you go to Tools, uh, let me just make sure it's not there. Ah, there it is. Okay, it's under wherever the extrude is on the surfaces. Wherever the extrude is, right here is the revolve. I didn't have to reset it. Otherwise, you go to Tools, Customize, reset toolbar, reset positions, etc. So shaft this thing about the Z axis by 90 degrees. 90. So what I have created here for you is 90 degree sector of that guy. Okay, you don't have to join it. If in doubt, join it. Okay, if in doubt, join it. There's nothing to join here. There's no need to join. Okay, so the other thing is material. We apply material. There's material, metal, steel on the part, and we say okay and save. There's my save. If you can't find your save, reset it or go to File, Save. Save. Okay. Now we're going to go to generative structure analysis. We're not going to use any fancy meshes. This is just standard basic default element that you have here. Let me change the rendering to material to shading, regular shading, and I'm going to select that. Make it a lot smaller, 0.1. How about that? Okay, you can look at your mesh, right click mesh visualization. There we are. Okay, deactivate it. Deactivate. Okay, so now let's apply the thickness to the property on this piece. Let's see what the thickness of this thing was. 0.025 inches. 0.025 inches. So change that to 0.025. 0.025. Good. Now the bottom, this bottom cannot go up and down. That's all. Sitting on a rigid surface, cannot go up and down. Okay. This is a plane of symmetry. Okay, now notice that right now, you see this? This is actually that line that I drew. The problem is that sometimes you put the stuff on things that are geometries, not edges. So hide this, hide this. There, now this is the edge. See that? Okay, so you user define, select this. Let's check it out. So this is symmetry. What is that? This edge lies in the YZ. So I'll write down YZ symmetry. I read it because it's, once you say YZ, it means that X is fixed. Okay? X is fixed. That is fixed. Rotations opposite. The other side is in the XZ plane. So let me make this XZ symmetry. XZ symmetry. Symmetry. And XZ means it does not move in Y, and rotations is opposite. XZ plane means it does not go in Y direction, and rotations opposite. Okay, what is the loading? What do we put here? It says 20 pounds. Now, if you took 20 pounds there, and you're taking a quarter of that, that's going to be 5 pounds on that top edge. So 5 pounds is the force. This is the force on that top edge. In the direction Z, minus 5. Minus 5. Minus 5 pounds, not 50. Okay, so let's see now. It puts it there. We can see that. See this? It's right there. Let me hide this guy for you. It's this going all the way around. Okay? Because this, we put this 5 pounds on that edge. So hypothetically, if there were 10 nodes here, on each one of them will be half a pound. So basically, we're replacing our load with the concentrated loads at these nodes. All right, so let's save this thing. File, save management. analysis, save as. Okay, so the folder is correct. The name I want to match this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Bernoulli, last name. It says homework 3, and then it says problem 2. That's the one you have to hand in. Problem 2, and then lab 54. 54. Yeah, and then whatever, analysis. Okay, and we're done. So let's run it. Hopefully we didn't forget anything. And it's going to compress down, nothing fancy. So there we are. Let me show you the deflection. Hang in there. Okay. Now, I don't like the way things are here at these corners because if this is a Belleville Spring, it should go straight down, right? And it should compress. I don't like the way. So this may look disconcerting, and I agree with you, and I'll show you why you get something like that. First of all, if you change the scale to 1, the true scale, what you're going to see really in reality is something like that. But it does bother me that the displacement here, you see that, is not the same as the displacements down there. That's because of the way you applied the load. As far as marking this homework problem is concerned, this is okay. There's nothing wrong with it. However, the way we applied the load here is not a realistic way. In other words, remember I said that when you say 20 pounds on that entire circle, because you have a quarter of a circle, it becomes 5 pounds on that. However, the 5 pound is divided equally between all these nodes, So hypothetically, if there is 10 nodes here and you put 5 pounds on that edge, on each node you put 0.5 pound. And this is not good. For marking purposes, this is fine because now I want to show you a different way of doing this properly. So I'm going to delete this distributed load, and instead on it, I will put something that we have never done before in the course. Over here, load, you see this, we have used pressure, we just used this, we have acceleration. This one we have not used. It says line force density. So you click on it, you select that edge, and you say, okay, on that edge, on that entire circle on the top, there is 20 pounds. So 20 pounds divided by the perimeter of this circle is going to give you, perimeter of the circle is 2 pi, radius is 0.75. So if you do that, if you take 20 divided by 2 pi times 0.75, you're going to get force per unit length, and it's going to get converted to this number, okay? This is Newton per meter. Since my units are pound per inch, the number that I gave you in pound per inch is going to be that. So let me run this thing. Let me run this. Instead of putting a distributed load, I put line force density. And now look at the deformation. Just look at the deformation now. This makes more sense. As far as modeling is concerned, a Belleville spring, you put some weight on this, okay, for example, some force on that, and it's going to get distributed properly. The moral of the story is this: for marking purposes, since we have not discussed this business of line force density, I said 20 pounds on the entire circle, you put 5 pounds on that, you're going to get results that don't look very good. This makes sense, whereas the other one did not make sense. So converting basically load into concentrate forces on nodes is not the right way of doing it. Don't worry about it. If you did it the first way, you're going to get full marks. Okay, so this is done. So save this. Now we're going to do our second problem. The second problem is, something like this. Use symmetry, use elements, appropriate elements, shell elements, of course. And the top is, top circle is clamped, and you put a pressure there, okay? What are the dimensions here? 4 by, what is that, 4 by 8? Okay, and 4 by 8. So let's go ahead and do this. We go here, we start, let's get rid of these. So, oh, by the way, for symmetry, because of the nature of the problem, we need only half of this. But I'm going to model the whole thing, and then we take half of it. So we start with the part file. Immediately save it. File, save management, save as, desktop. Oh, actually, we had this thing. This will be problem 1. We already created the folder in desktop. So this is problem 1. Okay. So on a convenient plane, on that vertical plane, I will sketch. Let me see now. I need this line, which is 4 inches, 2 inches above. Okay, so I'm going to draw a line like that. Where is it? Line. 2 inches up, 4 inches this way. 2 dimensions here. Oh, this. Control Z, Control Z, Control Z. I don't know, I want to delete this. Okay. Okay, cut it. Damn. Okay, let's try it again. This dimension I want to be 4, and this I want to be 2. Okay, exit and extrude it in both directions. Okay, by 8 inches. So we put a 4 here. You're going to get 4 inches on each side. Okay, now I don't have to join these already joined because of the way I made it. Now, however, I want to draw that circle here. By the way, while we let me cut this thing. On the top, I will sketch the circle. I'm going to draw my circle. That circle is presumably exactly halfway between, so we can do it like this. Left, control, right, control the middle center, center, equidistant, okay. What is the dimension of this? The dimension of that is radius 1 inch. Diameter 2 inches. Okay, exit. Okay, while we are at it, we're going to split that surface with this guy. We're going to keep it. Okay, now, on the horizontal plane, I will sketch that circle. Okay, that circle, half a circle, this. Okay. Where are we? Half a circle. I'm going to clean it up in a minute. Okay, this point, control that point. You're going to make it coincidence. Very good. Exit. Oh, yeah, I also want a line here because I want to fill F-I-L, F-I-L-L. That's semicircle. Okay, exit. And there is F-I-L-L. Fill this circle, semicircle. Now, these two need to be joined together because if I don't join them, the way we did it in class, there's going to be duplicate nodes on both sides, okay? Unless you create your, or unless you go to advanced machine tool or use analysis connections to fix it. Okay, I'm going to join that guy with this guy. So it's going to be a single surface. When I create element, it's going to be single nodes along the seam. Anything that I don't like, I can hide. Okay, there we are. So I'm going to hide this. I'm going to hide that. And while we are at it, we're going to split this. Split that entire joint with that middle surface. Doesn't matter. We keep one side or the other. Apply material. Metal, steel. We say okay. We save it. And we go to generative structure analysis. Okay. Let me change the rendering here. Okay, very good. We're going to measure the shell elements. Make it smaller. 0.3. We say okay. We can look at your mesh if you want. And because of what we did with joining, if you look at the element node numbers on the two sides, on this side and on that side, we have the same. See, 51 on the edge, 52 on the edge, on both sides. Okay. All right, deactivate this plot. All right, are these dimensions, are these thicknesses the same? I can't remember. I said, no, this is 0.2 and this is 0.4. These two are 0.4, this is 0.2. So first we're going to make 0.4 on everything, 0.4 inch on everything. And then we do a local 2D property on this piece, which is 0.2. So go to property, right click local 2D property. On this, we're going to put 0.2. I think that's what we had. 0.2 just on this. These are 0.4. Okay, very good. Okay, anything that you don't like, you can hide. I'm going to hide that. I think we put a clamp there. We put a pressure of, what is the pressure? You can see that. It's 10 psi. 10 psi. Check it out. This is the wrong direction. So change that to minus 10 psi. Okay, very good. Symmetry, don't forget, symmetry condition. You don't want to lose a whole whack of marks because you didn't apply symmetry condition. So let's uncheck all of these. These edges that I'm going to pick, 1, 2, 3, 4, these are all on the XZ plane symmetry. So this is XZ plane symmetry. Symmetry. As soon as I say XZ, means that it does not move in Y. And rotation is opposite. Now let's pick him. There, and there, and there, and there. Okay, let's save the analysis. File, save management. This, save as. Just like that, except that it's problem number 1. Oops, problem number 1. Problem 1. Save. Okay. I'm sure it's going to be okay. Run it. All right, here's the deformation. You don't have to be a rocket scientist to know this is right, or brain surgeon, or engineer. Okay, there's the deflection. Change the rendering. There we are. And to some of you, you might say that, stress is more important for me. There we are. This is the stress. We have no confidence in these numbers. Mesh conversion study has to be made. And basically, I have, in this course, I'm showing you the process. I'm not showing the accuracy and things like that, because those you have to do it when you work it out for your capstone project, or they pay you to do things and design things. Okay? Right. Okay, this is it, guys. So we are done with this homework problem. The only catch was that problem number two. Although we're going to give you full mark when when you put a 20 pounds or 20 divided by 4 pounds on that quarter of a circle, you get results that are not good, not reasonable. Okay, so when I converted it to line force density, which is the equivalent of pressure, okay, because remember, pressure is force density, surface forces that force density, okay, where that kind of a force that you put in beams on the top, not beams, on the top ring is line force density. Okay, this is it. We move into week 4.